Hi everybody, welcome to week 6. It's Monday. It is Endocrinology Day. So here we go. It's spring 2020. Off we go. Let me get my highlighter here before we go anywhere. All right, glucocorticoids. We're coming up to Cushing syndrome. We're coming up to a little section on gluconeogenesis. Oh, I hope you remember your biochemistry. I do like my gluconeogenesis. Okay, glucocorticoids. It's cortisol is the main one we're talking about, but you should know this by now. Released from the adrenal cortex, specifically the zona fasciculata. And normally it is stimulated by adrenocorticotropic hormone, ACTH. That comes out of the anterior pituitary. Remember who stimulates the release of ACTH? That would be CRH, corticotropin-releasing hormone. Really stimulates the corticotroph cells to make POMC, which is immediately converted by PC1 into ACTH. Real glucocorticoids. We're going to look at some synthetic glucocorticoids today. You'll run into those in practice. You need to know about those. But the real glucocorticoids are members in the production. Making glucocorticoids are members of the HPA axis, not the HP axis. That's the hypothalamic, which makes who? That makes CRH. And then pituitary, that'd be ACTH, and then cortisol comes out of the adrenal. So therefore, these three endocrine organs, hypothalamus, pituitary, and adrenal gland, make up the HPA axis. We have all sorts of functions. A very important and busy molecule. With regard to survival, gluconeogenesis, stimulating gluconeogenesis is probably the most important job because we have to have adequate blood sugar levels and glycogen levels, which are almost important. Those are tapped very quickly, turned into sugar very quickly. So that's one of the jobs of the glucocorticoids, is to stimulate gluconeogenesis and the packing of the liver with glycogen. And they're involved in protein metabolism. Really, protein metabolism, why do they are involved in protein metabolism? To make glucose. Why are they involved in fat metabolism? To make glucose. Stress, they defend against stress. We'll talk about that. And inflammation, they're very good at knocking out the inflammatory cascade. We will look at that as well. Today we'll look at that. It's kind of a short lecture today, but it's kind of meaty. The main glucocorticoid, of course, is cortisol. It exerts about 95%. I've seen 90% in some authors, but about 95% of all glucocorticoid activity in the body specifically comes from cortisol. It does have mineralocorticoid activity. What? Because when I say mineralocorticoid, what's the first thing that pops in your head? You better have said it by now, or you're not studying hard. I'm worried if you don't know that. That's aldosterone, right? Aldosterone is the one that has mineralocorticoid. It is the big mineralocorticoid. But I think I said before, cortisol can actually bind to mineralocorticoid receptors or MR receptors as well. What? I didn't screw that up. Cortisol can bind to mineralocorticoid receptors. Aldosterone's ability to bind to those receptors, its mineralocorticoid affinity, the ease of which it binds to those receptors and stimulates a response, is 3,000 times greater than that of cortisol. There are some molecules we'll look at that interfere with cortisol's attempts to bind, especially in the kidney. Nevertheless, some of it can still bind. And then when you take that into account, the plasma concentration on a daily basis, so the average plasma concentration of cortisol is 2,000 times that of aldosterone. So definitely a little activity, little mineralocorticoid activity is a result of cortisol. Not on the kidney so much, though. Guyton, a board book here, some fun facts. So 90% of cortisol is actually carried via a corticosteroid binding globulin. Albumin actually carries a little bit as well. 10% of it is free and naked in the bloodstream. That stuff is immediately used. The cortisol that is bound can actually be stored, and you can build up a little reservoir of that, and it can be tapped if needed. And cortisol binds with very high affinity to its receptor, glucocorticoid receptor, specifically, though, alpha glucocorticoid receptors, or sometimes they're called type 2 corticosteroid receptors. Right? These corticals, remember, a lot of receptors sit on the cell surface, right? Here's a cell surface. There's the nucleus where the genetic material is. There's a cell receptor here. So a lot of ligands or hormones bind to the cell. That's not true with these glucocorticoid receptors. They actually float around inside the cytosol. Why is that? Well, because cortisol is a steroid. And how's the cell membrane? I mean, that's a lipid bilayer. It's lipid. So is this. It can go right through there super easy. And so it binds to its receptor that is floating in the target cell. And there's many target cells. But the two of them together, once they're bound, they have the ability to go right inside the nucleus and go right into the DNA and bind to genes and turn some genes on and some genes off. So that's the way cortisol works. Okay, and its effect again is on those alpha glucocorticoid receptors, or GR is a common. On board you won't see that. It's got to be written out. Type 2 corticosteroid receptors is another, aka from the National Institute of Health. Okay, we said its target is in the cytosol. The binding takes the complex into everything I said, into the nucleus. Who covers these binding sites? Right, here's a receptor, here's a GR receptor floating around. There's actually a heat shock protein that covers that. And it also discourages, if mineralocorticoids can bind to these too, it discourages other things from binding to these. But when the cortisol gets near, it falls off and gets out of the way. That activates this so they can bind up. We won't get in. There's some disease of heat shock. You probably have heard of that in biochem, but we won't go down that rabbit hole. There are beta-glucocorticoid receptors in the body. They do not bind to beta. They only bind to alpha-glucocorticoid receptors. We won't talk about betas right now. And as noted, cortisol can also bind with less affinity to mineralocorticoid receptors as well. Well, I know what some of you are thinking. Mineralocorticoid, let's see. Those are the ones on principal cells, right? That's what aldosterone binds to, and that we talked a ton about the binding of aldosterone to MR receptors and how that stimulates principal cells to do their things, to uptake sodium water and kick out hydrogen ion and potassium, kick it out into the filtrate, pee it out. So now I know what you're thinking. It's like, oh my God, so can cortisol actually bind to principal cells? The answer is normally, with quotation marks, no. The kidney and other tissues in the body as well, not just the kidney, but the kidney is really dense with a certain enzyme. And the enzyme is called 11-beta hydroxysteroid dehydrogenase type 2. On the test, I'm just going to call it 11B-HSD2 because that's a mouthful. But maybe I'll say it now. You never know what I'll say in the test. That's a very important enzyme. That one is able to bind with cortisol in the kidneys, and it turns cortisol into a more harmless, not very active molecule called cortisone. So the cortisone can kind of just hang around there and do really nothing. If you need to, however, though, this is a two-way enzyme, so you could convert the cortisone back in to cortisol if you wanted to. It's a two-way enzyme. But cortisone can't stimulate principal cells, so you don't have to worry about it doing anything there. Who cares about 11-beta HSD2? Patients with a rare disease called apparent mineralocorticoid excess syndrome, or AME. If you're doing med-legal reports, agreed medical examination is AME. That's your goal, is to have the insurance company's attorney and the patient's attorney agree to use you to settle your case. That is your goal, to become an AME if you're into that stuff. It took me 7 years before I was able to achieve that goal, so it's not easy to accomplish. Anyway, so what's the deal with AME syndrome? Super rare. It's autosomal recessive disease. And these patients have a mutated 11-beta HSD2 gene. Uh-oh, now we're in trouble. So therefore, their normal release of cortisol, there's nothing wrong with their adrenal gland or anything else. Nothing wrong with their principal cells. The trouble is, without 11-beta HSD2 around, aldosterone, cortisol will affect the principal cells. It'll bind to the mineralocorticoid receptors, just as easy as aldosterone. So now you got two ligands stimulating the kidney. So these people, well, you can guess. Tell me, what do you think how's their blood work? What's their problem going to be? Well, aldosterone's not around all the time, right? That's only, it only's turned on when hypovolemia. It's turned on by angiotensin II. But, I mean, cortisol is released all the time, right? You always have cortisol released. So you're always going to have your principal cells running. So you're going to have too much water and too much salt are going to be taken up, right? Sodium chloride. Too much of these are going to be taken up from the filtrate. Here's the proximal convoluted tubule. Distal convoluted tubule, connecting tubule. Yeah, where principal cells live, connecting tubule is better. Yeah, so it's taken up. So what's that going to do to your blood pressure? You're going to have hypertension. So that's the problem. AME patients, they have hypertension. They have, and who goes the other way? Who gets kicked out? Salt and water come in. Who gets kicked out? Just said it. Potassium. Good, and hydrogen ion. So if you can't kick out, or if you kick out too much hydrogen ion, you become alkalotic. You have metabolic alkalosis. Your blood has too high of a pH. You're too basic. You also have, if you kick out too much potassium, now you have hypokalemia. What about renin? Well, if you have hypertension, you're certainly not going to have the R2A system turned on. So you have low levels of renin. You'll have low levels of aldosterone because you have low levels of renin. So clinically, you'll have all the same kind of symptoms. I won't go. We've already talked about the symptoms of the clinical presentation, but it's really tough to tell apart until you get these two results back right here. Then you can tell them apart. But I mean, it really looks like it's acting like hyperaldosteronism. Licorice, what in the heck? Yeah, that's right. There is a syndrome where people eat too much licorice and they can actually develop AME. So I won't get into the biochemistry of it, but there's molecules within licorice that once they get into your small intestine, they can be converted to an enzyme called glycerintinic acid. Glyss, like bliss, glycerintinic acid. So what? Who cares about glycerintinic acid? Well, glycerintinic acid can actually bind to our 11B HSD2 and knock it out of action. What did that enzyme do again? Well, that converted cortisol into cortisone, that harmless cortisone. So same thing. Your principal cells are going to be way overstimulated because cortisol is not being converted to cortisone in your kidneys. Got it? All right. AME versus hyperaldosteronism. Very hard to tell about. Again, everything we said. Clinical testing shows that this difference. Hyperaldosteronism has high levels of aldosterone, high levels of renin. Right? It's driven by R2A system turned on too much. AME will have low levels of aldosterone, low levels of renin. We already discussed that. Let's meet the glucocorticoids. We know them already. How many times are we going to meet these things? But let's meet them again. Cortisol. Sometimes in AKA it's called hydrocortisone because it is similar to the cortisone molecule. This is the principal mineral corticoid or glucocorticoid? Who's the principal mineral corticoid? Again, aldosterone. Good. Counts for 95% of, according to Guyton, glucocorticoid activity. Is super potent. Not as potent as some of these synthetics we're going to talk about. And it does have some mineralocorticoid activity. The other one is called corticosterone. That's also secreted. It's much less potent than cortisol. It has insignificant glucocorticoid activity because it's so weak. I just said that. Counts for only 4% of glucocorticoid activity. The one thing that's weird about this, remember our biochemistry, our adrenal steroid, the birth of adrenal steroids, that pathway from cholesterol. Remember aldosterone, corticosterone is in the aldosterone pathway. It's one step away from becoming aldosterone. Right? Remember this thing? So cholesterol, that's the rate limiting step. Did I tell you guys that? Of this pathway? This very first step is the rate limiting step. That old cholesterol demylase is the enzyme. You have a cholesterol demylase, you're born with a deficiency in that or a mutation in that gene, you will die. You won't. These kids don't make it. But anyway, look at the pathways. So I won't go through the whole thing. We talked about 21-hydroxylase quite a bit, how important. Very common mutation. Well, super common, but it can happen. But right here, so here's cortisol. And how come you would think corticosterone would be right here? But it's not. It's over here. So that's pretty strange, isn't it? It's in a different pathway. So you would think it'd be one step away from here, but it cannot be converted into it. It's its own person. And one step away, you got yourself a mineralocorticoid, aldosterone. So really strange. How about some more glucocorticoids? Cortisone, we just talked about that. That's the one cortisol can be converted into this less potent form by 11B-HSD2. Talked about that. Prednisone, now these are synthetic, so these are all medications. Prednisone, I talk about that a lot. It's 4 times as strong as cortisol. So methylprednisolone is 5 times as potent. Look at this one, dexamethasone, 30 times as potent and very long acting. This is a very powerful for people with Addison's who don't make cortisone. They can use that and use for other stuff as well. And then hydrocortisone, that is the least potent, but used a lot for patients. So it's a good one to take because you can kind of vary the doses and you can fine tune the dosage with this one. It is shorter acting as well. So that's the one that people with Addison's disease usually end up taking. But there are some super powerful ones. Dexamethasone is used for epidural steroid injections too. Yeah, and there's more of them. I just stopped the list right there. So the synthetic glucocorticoids have actually been around a really long time. Back in 1949 they were discovered. Used for all sorts of inflammatory conditions. They're very good at breaking the inflammatory cascade, as we We've looked at that a little bit, but we'll take a quick peek at it again. Including chronic sciatica. I mean, glucoprednisone is commonly used for the treatment of sciatica or any other radiculopathy, whether it be lower extremity or upper extremity or thoracic radiculopathy, radicular pain. It's used for all that stuff. How do the glucocorticoids knock out inflammation? Oh, you're going to be sorry. You shouldn't have asked that question. Well, there's glucocorticoids can go into the nucleus of the cell and manipulate genes and do it that way, or they can flat out go and bind to a T lymphocyte and knock it out like that. So there's genomic, where they go into the nucleus and manipulate the genes, and there's non-genomic, where they just go bind, like the beans. Who are the beans? Basophils, eosinophils, neutrophils. Those are all the segmented granular white blood cells, right? They have granules that can be released. It's like poison for bugs. It kills bugs, those granules, and those granules call in other troops of the inflammatory cascade. So let's look at some of the genomic effects. So they turn off, which is called trans-repression. So they can trans-repress genes directly by going into the nucleus and turning off, well, who better to turn off than the cytokines? Specifically the pro-inflammatory cytokines, which are like gasoline, especially this one right here. It's a lot of sciatica research done on that, tumor necrosis factor, alpha in particular. But these are all, I mean, if you're fighting an infection, you got to have these on. If you have COVID-19, these guys are on. That's the trouble, though, with COVID-19, right? You get a cytokine storm going on, and this can just take over your body. It can inflame everything. That's the problem with these things. But they're great, but you don't want them turned on for too long. So glucocorticoids will directly go into the nucleus and bind to the genes that make interleukin-1, 2, 6, 8, tumor necrosis factor, especially alpha, interferon gamma. They also can turn off directly inflammatory molecules like COX-2, prostaglandins. Remember that? Prostaglandins, remember that cascade we talked about? Here's two. I mean, this is the big heading right here, but both of these are very important in the inflammatory cascade. COX-2, of course, is an enzyme. Prostaglandin is a product made by this enzyme, phospholipase A2. So it can also turn on some genes that create some anti-inflammatory cytokines. These cytokines actually turn off the pro-inflammatory cytokines, interleukin-10, lipocortin-1, and NFKB. That's actually gamma, right? It's supposed to be gamma, I think. NFK, we'll just call it NFKB inhibitor. And then they have the ability to bind right to phospholipase A2 and knock that thing down. Remember, that's the kind of the head of the entire inflammatory cascade is this enzyme. So that's this enzyme through COX-2 makes tons of prostaglandins. Remember PGE2 we talked about. Remember that inflammatory pathway, right? Excellent video. You can check that one out. I like the way he explains it. But yeah, phospholipase A2 makes arachidonic acid, right? That's in a blood vessel that's involved in the inflammation, where it comes right from the cell membrane. Phospholipase A2 takes part of the phospholipid from the cell membrane, converts into arachidonic acid, and then we have the COX enzymes can create all sorts of proteoglycans, or not proteoglycans, all sorts of prostaglandins, which have all these effects, right? I'm not going to go through this whole thing. We already talked about that. But look, these are all inflammation. Look at inflammation here, inflammation here, inflammation over leukotrienes. I mean, it's everywhere. So If you snuff it out at this up at the very top of the cascade, you get all these effects, which is cool in some ways, but in other ways, like with platelet aggregation going down this pathway, because once you snuff this out, all these arrows change directions, so you can get increased clotting. You have to be careful of that. That's what happened to not Celebrex, but Vioxx caused clotting, especially in the heart and things like that. All right, I'm not going to go back there again. There's just another pathway. It's got more of the PGEs and prostaglandins, different types of prostaglandins in here, and leukotrienes. All right, what about inflammation? What about other mechanisms? This is from Guyton. It stabilizes, toughens the lysosomal membrane. Remember the lysosome, the little Death Star that's inside of a cell. Well, one important mechanism in the inflammatory cascade is to break open that lysosome, destroy the Death Star, and then all of those evil digestive juices and those molecules will be dumped out into the inflammatory soup. Well, one thing cortisol does is it toughens up that membrane of the lysosome, and so the normal inflammatory process can't crack open the lysosomes, can't tap into its destructive power. Capillary permeability is important for calling in monocytes and other things like that. They need to be able to squeeze out of the capillaries, and so it decreases capillary permeability. That's another way that it kind of can help snuff out the inflammatory cascade. It decreases white blood cells and their ability to phagocytize. We talked about it blocking phospholipase A2. Therefore, it blocks the formation of leukotrienes and prostaglandins. Before I talked about that, that should be in its own category, I think. And then fever, just to throw that in there, it also knocks out fever by interleukin-1, stimulates hypothalamus, the temperature centers there, thermoregulatory centers, and that's so it reduces fever. What about some adverse effects for glucocorticoids? Well, we talked about COX-1 inhibitors, how they knock out PGE2 in the stomach, which we need for stimulating the gastric mucosal barrier. Remember, it stimulates the mucose cells, or the columnar epithelial cells. It stimulates them to create mucus, amongst other things. It also turns off histamine release. And so COX-1, one reason your stomach doesn't last too long on COX-1, because it knocks out PGE2. PGE2 is also one of the prostaglandins involved in the inflammatory cascade. So great, it subsides inflammation as well. But the cost is I guess we could go back to this. Where's PG? COX-1 is right here. So COX-1 enzyme does all this stuff. Normally, it stimulates inflammation, pain, fever. It makes the gastric mucosal barrier. So if you knock it out here, all this stuff reverses. It decreases inflammation, decreases pain, decreases fever, but it also decreases the gastric mucosal barrier by decreasing the production of mucus, and histamine gets increased. Right? See how you have to know all that stuff? This stuff all kind of piles up on each other, doesn't it? Let's see. Yep. Okay, so we talked about that. Long-term use while you're taking the glucocorticoids, you can develop Cushing's syndrome, right? If you have to take so much that you're over physiological dose, it's just like secreting too much cortisol. Right? Too much cortisol, I mean, that is overproduction of cortisol, and the glucocorticoids is Cushing's syndrome, which we'll get to tomorrow. Yeah. And then when you're coming off or trying to come off, remember it said while you're on this stuff, it makes your adrenal gland atrophy, or the zona reticularis zona fasciculata, those are the ones that atrophy, but they may never come back in some people. And you can't tell who has a strong adrenal gland and who doesn't. But while you're coming off, you're going to have adrenal insufficiency, right? Secondary adrenal insufficiency, right? I don't need to talk. We talked a lot about that already. How about some more fun facts? Glucocorticoids, we know this already, have both glucocorticoid and mineralocorticoid activity. Hydrocortisone has a lot of mineralocorticoid activity. The exception is dexamethasone. That's the strongest one of the strongest synthetics. Did we talk about that one? I think I did. It has almost, for whatever reason, it doesn't find the MR receptors bindable at all. It just has no interest in them. So that's another reason you could use that one. So all of the synthetics are different, have different actions, just like Vioxx versus Celebrex. Celebrex is a COX-2. Vioxx was a COX-2, great anti-inflammatory, but it was increased heart attacks and stroke because of its clotting problems. Celebrex is a very similar molecule, yet it has been around for a long time now. It doesn't have those properties, even though it's the same class of molecules. Like all steroids, we know this already, glucocorticoids come from cholesterol. The only difference between, I don't know what I'm trying to say here. Glucocorticoids in stress is another important thing. Glucocorticoids affect virtually every tissue in the body. We know that. Therefore, they have a lot of functions. But one of the key functions, as I've said a couple times now, is to make sure you have enough glucose levels in your blood and have enough glycogen reserves. That's their job, is to make glycogen storage and then, really make sure you have adequate glucose levels. Why do you need that stuff? This caveman will tell you. He's being chased by the saber-toothed tiger. His adrenal gland is cranking out cortisol like crazy right now because all his muscles are using up all that, the available blood glucose. And where's that going to come from? It comes from cortisol, but you can deplete your cortisol supplies or your glycogen supplies can be depleted very quickly. So glucocorticoids will keep cranking out glycogen and stimulating production of glycogen. This is all accomplished. Getting blood glucose in the blood is accomplished through a process called gluconeogenesis, which we are going to talk about. What are some glucose-sucking stress events? Major traumas, infection, chronic exposure to really cold or really hot environments can do it. Surgery can do it. Severe illness, pathology can do it. Here's an interesting one for all us who are locked in the house. Like I've been locked in the house. My wife's the only one who's gotten out to get food and things like that, but I'm at more high risk, so I just stay in the house pretty much. So chronic confinement can start to be a stress and start sucking up your glucose. And what's that going to do? All of these are going to increase your cortisol. As stress increases, so does the blood cortisol levels. All right, everything I said, stress event sucks up the glucose as well as glycogen, robs that blood glucose, which you need. Everything I said. You go into that's the problem too, right? You go into hypoglycemic shock. People coming off corticosteroids, they have to be very careful. You have to taper very slowly for those things, or you could easily go into hypoglycemic shock. And sometimes it's hard to predict which ones. It's sometimes hard to predict how quickly your adrenal gland will come back. Usually people on a 10-day course of 5 milligrams or maybe 10 milligrams of prednisone, they're usually not going to have problems if they taper down, but you never know. According to that, remember that one study, even people less than 5 milligrams, some people, not many, but some people, it took their adrenal gland years to come back on, and some of them didn't come back on from a simple dose like that. So they're nothing to mess around with for sure. What's the answer? What's the body going to do? We already said that. It's going to make more glucose. How do you make more glucose? You release more cortisol. How do you release cortisol? Corticotropic releasing hormone, adrenocorticotropic hormone, and it makes ACTH, and that binds and makes the HPA axis, right? Cortisol quickly stimulates gluconeogenesis into gear. And then we're going to start talking about gluconeogenesis now, which I do like. Remember, brain cells and blood cells, they don't store glucose. They have to have it around in the blood. That's the only place they can get it from. So that's why you have to have adequate blood glucose levels, because of the noodle, the brain. The biochemical pathway for making glucose, or what is gluconeogenesis? It's a biochemical pathway that makes glucose from non-food precursors, right? We usually get our glucose from eating food all the time. But what if you burn up so much glucose and you're in between meals? What are you going to do? You got to be able to make it in other ways too, and cortisol is the way you can do that. And gluconeogenesis can take non-food precursors like muscle. It can tap into the muscle to get amino acids, except for leucine and lysine. The two L's don't participate in this pathway. Alanine really is very prominent in this pathway. Glycerol is you can break down fat, and lactate. You can even use that waste product, lactic acid and lactate, to make glucose by running it through the Krebs cycle, as we'll see, and then running it through gluconeogenesis. Normally, gluconeogenesis occurs in the liver about 90% of the time. The liver is where it's cranking and working, but that's not the only place. The kidneys can run gluconeogenesis as well. In fact, they always are running it a little bit. But if you go into a fast, the kidneys run gluconeogenesis to a much higher degree. So it's fasting where the kidneys actually are important for helping you make blood glucose. How does cortisol stimulate gluconeogenesis? Well, a couple ways, more than a couple ways. One, it kind of just said it breaks down fat and muscle. Fat is broken down into fatty acids and glycerol. So you remember from your biochemistry that glycerol we can run glycerol through gluconeogenesis, but fatty acids cannot be run through gluconeogenesis, or the Krebs cycle for that matter. Right, that's an important one, and we'll look at this more in the next class. Muscle proteins can be broken down. In fact, cortisol, weird thing about cortisol though, right? You guys had this a little bit before, I think. Remember the weird protein breakdown pattern that you get with cortisol? It loves the arms and legs, but it doesn't like the trunk that much. So you get an uneven breakdown of protein. So you get the classic, quote, spindly arms and legs. Justin, if you're watching this, we had a kind of inside joke about that. I guess he was spindly arms. But yeah, so they look really weird with these skinny little arms and legs, yet they have a normal or even a pendulous belly in some cases, like a Homer Simpson belly. So a very strange breakdown pattern. How does cortisol stimulate gluconeogenesis? It can also make enzymes, because one of the keys to running gluconeogenesis is running the Krebs cycle. And so it goes into cells and stimulates the making of all of the enzymes for the Krebs cycle. If you have tons of enzymes around, then there will be no delays. The Krebs cycle will be running full power. And what's the key product of the Krebs cycle that we care about? Mainly oxaloacetate. Right? So how does it do that? How do you make oxaloacetate? Well, you can run pyruvate completely through the Krebs cycle and make oxaloacetate. We'll learn about it. You can take pyruvate, and what's pyruvate, by the way? I assume you know what that is. What is it? Where does it come from? that's glycolysis, right? That's the end product of glycolysis. So what do we do with that end product? We can't run it backwards, right? We just can't go backwards through glycolysis. We have to either run pyruvate all the way through the Krebs cycle, or there's a direct way, which I'll show you, where you can take pyruvate and convert it directly into oxaloacetate without even going through the Krebs cycle. And then, of course, oxaloacetate is run almost you can think of it as backwards through gluconeogenesis, or backwards through glycolysis, because many of the same players are there. But there are some steps that we need to, irreversible enzymes that we need to get around. So therefore, they just call it a new pathway. But really, it's mainly glycolysis. So if you've memorized the glycolysis pathway, which I'm sure you have, gluconeogenesis is quite similar. All right. What else? How else does cortisol stimulate gluconeogenesis? Well, how about it makes so we just said it makes more enzymes for the Krebs cycle, so that will run full power. It also makes enzymes for a gluconeogenic pathway as well. So that can run full power, not run out of enzymes and then have to make some from scratch. Okay, gluconeogenic, these are the enzymes that run gluconeogenesis. Cortisol stimulates gene transcription of these to crank out enzymes, everything I just said. All right, I think I'm going to stop it right there, but here's where we're going. So make sure you review your biochem notes so you won't be completely lost here. And you guys got part 1 boards coming up too, right? So this is not going to be a waste. All right, I'll see you tomorrow.